and welcome back. So now it's almost 1 a.m. and we're gonna keep moving, buddy. We're gonna keep moving. So for this next example, again, we're gonna for a while now, we're gonna just continue to just practice the transformation. Okay, we're gonna practice the transform, and then we'll start to chat more and more and more about it. This next one, this next transform, I'm going to set it up, but this would be one of those. This would be one of those integrals where you would use a table. You might also be able to do it with other techniques, but I'm going to just give you the answer. And the reason why I'm showing you this is because later I'm going to come back and use this portion here for some other problems. Okay, so nevertheless, one more time, let's just go ahead and set this up. So we want to find the Laplace transformation of sine of bt, where b is some non-zero constant. So again, this is your function to that which you want to transform. So we're going to jump right to the limit with n going to infinity, 0 to n, and of course, remember, it's just e to the negative st multiplied by your function. So e to the negative st, and now you can just imagine that this sine of bt is going here. So multiplied by sine of angle BT. All right, and that we are integrating with respect to t. So as I said, you can kind of tell you would need there's a few different ways of doing it, or you would use a table. Nevertheless, let me write the result. Okay. So the result would be the limit as n goes to infinity. And here would be, we'll jump right to the part where we're going to jump right to the solution in just a second. But let me at least show you the integral. So the integral would be e to the negative st over s squared plus b squared multiplied by negative s sine of angle BT minus b cosine of angle BT. And we would be going from 0 to n. All right, so at this stage, what you can imagine is n is going to be inserted in for the t variable, as will 0. Now again, I don't want to waste a lot of time with this part, because what you would find, and well, I would encourage you to, if you feel like you could benefit from some practice, try that f of n minus f of 0. And then at some point in time, you should be able to take that limit of n as it goes to infinity. And when all is said and done, this is what you're left with, s squared plus b squared. And that's true for all s greater than 0. Okay, so I grant you I didn't spend a lot of time here, but I wanted to show you because I'm going to come back and we're going to use this in a little bit. So we're going to just put a pin here, put a placeholder here for now, and let me show you other types of functions that you can transform. After this next one, I think it's about time to start to talk to you about the transform, okay, about this Laplace transform. But one more. So the power of this transformation, well, I'll speak to it for just a second. But for example, it can be, since it's linear, it can be applied to under some certain conditions. It's really good for any type of jump discontinuities. I mean, like this is what a piecewise function, right? So in other words, to make sure you understand this, f of t equals 2 if you pick 0 from 0 to 5, right? For all values of t between 0 and 5. F of t is equal to 0 for all values of t between 5 and 10. Now, f of t is equal to e to the 4t for all values of t greater than 10. But what happens is the 5 and the 10 are basically jump discontinuities, meaning like if you could, if you have continuity, you can draw your curve without lifting your stylus, right? That's continuity. But if you have some type of jump discontinuity, it would mean that you have to pick up your pen or your marker to be able to draw that curve. So what we're going to do is let's go ahead and talk about how-to, right? How do we transform this function? And well, so remember that the Laplace transformation deals with that 0, or basically something to infinity, right? That portion to infinity. So this is a finite. This is bounded in a between 0 and 5. This is bounded between 5 and 10. It is actually not bounded in the sense that doesn't include 0 or 5. So maybe I misspoke, but you can, in other words, you can see that in terms of moving to infinity, it's only with the e to the 4t that you're going to have that improper integral. All right. So how do we do this? How do we do a piecewise function like this? Well, what we're going to do is we're going to break it up. So f of s, we're going to break this integral up from 0 to 5, and then from 5 to 10, and then finally from 10 to infinity. So each one of these each one of these is going to be a Laplace transformation. What I misspoke earlier, what I meant is the only one where you have to worry about the limit is that last term. So I can't remember quite what I said, but I think I misspoke. If I didn't, then no problem. But for everything else, let's think about it. So the very first, so dt, dt, dt. So the very first function is 2. So it's going to be e to the negative st multiplied by 2. And multiplied by 2. All right, of course, the next one is going to be e to the negative st. And now your function is, for the second piece of your piecewise, is just f of t is equal to 0. And for that final piece, you have e to the negative st. And for that final piece, of course, your function is equal to e to the 4t. Okay, so let's go ahead and start to think about how we would integrate each of these. So with this first one, with this first one here, we can, of course, we can bring that 2 out front. And then what you would do is you can integrate that by just letting u be defined as negative st. And we've already talked about this. Du would just be negative s dt. Okay, so we're going to go to the next one, but just remember that I would have to multiply and divide by that negative s. Now, with this next integral, this is simply the integral from 5 to 10 of 0 dt. And of course, if you integrate 0, you just get a constant. You just get c. Right? But you and I know that or you can think of it like this. Like you're just going to get plus c, right? But through the well, I don't put it. It's going to equal 0. My apologies, but just simply because you can imagine that those constants of integration always cancel out when you're doing definite integration. So this is just going to equal 0. Very easy. All right, this last one, we're probably going to want to, let me think about this for a second. We're probably going to want to go ahead and combine. So if you have e to the negative 5t and 4t, no, look at me. Remember I told you a second ago that I confuse my 5s and s's? I do that with my own notes. I'm really got to be careful here with the stylus. Listen, if you hear me say negative 5t, just assume that I mean negative st. All right, because I am going to lose my brain. All right. So yeah, this is easy. It's just going to be, I'm going to do this in one swoop. So this would just be e to the negative st plus 4t, right? And then from that, we could factor out a negative t. So that's going to be e to the negative t multiplied by s. So, yeah, because if I factor out a negative, that's going to be a positive s, and now that's going to be a minus 4 dt. All right, and that's not bad. That's just back to u substitution. So u can be negative t times s minus 4. Du would just be negative s minus 4 dt. All right, so at this stage, just imagine that I'm going to have to multiply and divide by negative s. I'm going to have to multiply and divide by negative times s minus 4. So I'm going to do all that right now, but the good news is this just ends up being e to the u, and this just ends up being e to the u after you do that constant multiple rule. So let's go ahead and get there. So we remember we brought the 2 out front, and we have to multiply and divide by negative s. So let's do negative s. All right, and let's go ahead and e to the u. The integral of e to the u is just e to the u. So let's back substitute. So that's e to the negative st. And of that, we're going from 0 to 5. Now this is going to be plus 0. All right, and because that's from this this middle integration. And then from here, we got plus, and this is going to be one where we're going to have to, it's an improper integral. So it's going to be the limit as n goes to infinity. And remember, we have to multiply and divide by this s minus, this negative times the s minus 4. So I got to have that 1 over negative times s minus 4. All right, so that's outside of the integral. And the integral was 10 to infinity, but now it's going to be 10 to n. Actually, you know what? There's no need to have this step. I can integrate this right now, because this is just where all we would be doing is integrating e to the u. Very simple. So if I integrate e to the u, I just get e to the u, and I'm going to back substitute. So that's going to be e to the negative, so negative t times s minus 4. And now we'll be going, instead of 10 to infinity, now we'll be going from 10 to an upper bound of n. All right, so hang out for just a second, as if you have anywhere else to be. And 1 o'clock, well, you're not watching this at 1 o'clock. But as if you had anywhere else to be, hang out. Let me just make sure I didn't insert anything that I didn't want to insert. All right, perfect. So at this stage, I'm probably going to grab this and move to the next page so I have more space. All right, so at this stage, it's time to use that definite integration, so that f of 5 minus f of 0. Of course, this is all going in for t. And this is going to be f of n minus f of 10. Okay. And here we go. So what is that going to look like? So let's start with plugging the 5 in for the t. So what does that look like? That's going to be negative 2e to the negative. This is so weird. Look at this. I got to have a 5 beside an s. Of course, they would pick a 5. And that's got to be over s. All right. One more time. So we have a negative here. We have a negative here. So that's going to end up being plus. And of course, when you plug in a 0, that's just going to be 2e to the 0 over s. All right. Plus, let's go ahead and, we haven't done the limit yet. And let's go ahead and do this. So now we're going to be plugging in here for t. So that's going to be negative e to the, it was a t, but now it's negative n s minus 4 over, so it doesn't matter if you keep that, this negative symbol here can stay in the denominator, or you can move it to the out front. It doesn't really matter. So in that case, it would be over s minus 4. Again, You got your negative here and negative here, so that's going to be plus. And now we'll be plugging 10 in for that t. So that's e to the negative 10 times s minus 4 over s minus 4. Okay. So where are we in this problem? Well, of course, this whole term moves to the denominator. And when you evaluate that n to infinity, that is just going to be like having e to the infinity, which makes that whole denominator infinity. Okay? So in other words, all of this is going to zero out again. What you're left with is your answer. So your Laplace transform is simply equal to negative 2e to the negative 5s over s. And that's going to be plus, well, 2 times e to the 0 is just 2 times 1. So 2 over s. And then finally, since this goes to 0 with that limit, it's going to be plus e to the negative 10 s minus 4 over s minus 4. All right, and of course, this is true. Let's see here. For this case, it would be true for all s greater than 4. All right, now, let's start to unpack a little bit more of this Laplace transform, right? Because, I mean, at this stage, hopefully you're starting to feel okay with the transform itself. Let's start to point out some things. So I'm going to go back a page. So like I said previously, notice that you start with an f of t, right? You start with a domain of t, and after this function undergoes this transformation, you end up with a function of s, right? The s, you go from domain of t's to a domain of s. That's interesting. Now, remember that we also said that when you draw this curve, right? So if you think about it, from 0 to 5, f is just 2. But then right there at 5, it jumps down to 0. So notice that there is a discontinuity here and here, right? What we call a jump discontinuity, where you have to, in other words, you have to, when you're drawing it, you have to literally pick up your pencil to keep drawing it. So there's a jump discontinuity here at 5 and at 10, and let's go back and let's see that 5 and 10 are showing up in our Laplace. I'm sorry, yeah, so our Laplace transformation. Now, that also is interesting. Let me now, so let me think, where do I want to go here? I don't want to take a break, not yet. So, okay, let me talk to you a little bit about this transformation. So, the Laplace transformation, it's been around for a while, but it hasn't been applied to, the technique hasn't been applied to differential equations for very long. So Laplace was Pierre Laplace, I believe, yep. So this is near the 1800, right? This is somewhere in 1790, 1780. I better not write it yet. So it's before, 10, 20 years before 1800s is when Laplace introduced this technique and this transform. And so, but Laplace was doing work in probability. So Laplace wasn't seeking to, or just didn't see all the implications of this transformation and where else it could be used. So it wasn't until the 1900s, right? Maybe like 1920, 1930, before this technique started to make its way into differential equations. And because I've taken, I've taken graduate work in mathematics, and I've taken graduate work in economics, and I've even seen in my graduate work in economics classes Laplace transformations. So all of this to say, well, what actually does the transformation do? So recall back in, this would have been back in chapter 4.4, where we were studying second order differential equations, and I'm just making up something here, say plus 3y, and remember they were equal to some function of t. Now this is when we had to use that method of undetermined coefficients to figure this out, right? And it was labor intensive, if you remember. It took a long time just to find the right form, right? The right form for to even apply the undetermined coefficient technique. So that was painful. But the Laplace transformation, okay, can get you to your y equals, right? Can solve your differential equations without having to do all, you don't even have to take derivatives. You don't, or at least the derivatives of trial solutions, you don't have to break it up. You don't have to think about the right form for the method of undetermined coefficients. It is a huge time saver. It truly is. The drawbacks, and this won't really apply to you unless you continue in your study of mathematics. Like the drawbacks of this type of transform is it's not very helpful. Well, it's not helpful at all, really, for equations if they have like nonlinear equations, or if they're you got variables for coefficients, and you'll see that sometimes even this technique can just be painful, but for a lot of the problems that a lot of problems that we did, in other words, if I went back to 4.4 and I taught you this technique, and then I taught you the method of undetermined coefficients, and then said you get to pick which one you want, I guarantee you every single one of you would have gone with this technique, because the Laplace transform is a lot faster and it's more of an algebraic approach. Now, that is kind of the why, okay? So we could use it on we can use it on compartmental analysis and all types of other applications, but that's kind of the why. That's the why do people study this technique? Why must you learn it? And hopefully that at least gives you an idea. Now, what I need to do for just a little bit of time before I take another break is I want to discuss some of the properties of this type of transformation. Right? So clearly you can imagine that you start off with some f of t function, right? But this function gets transformed, right? This Laplace it's an operator, right? It's going to operate on this function f, and the result has some very specific properties that are useful to us. Now, when I'm talking about properties, listen, everything I'm talking about is a time-saving technique here. So I'm not just going through various algebraic properties, and I want to show you how you can do a lot of things with this transform, and I want to make sure you can put it to its full potential. So the first property that you want to make sure you understand is that these transformations, these Laplace transformations, are what we call linear transformations, right? Or linearity. So what I mean when I say that they are linear, if you don't mind, just to kind of paint you a picture. So forget about Laplace for just a second, okay? Let's assume that you have some function f and you have some function g, right? Now, let's just make up something. Let's say f is defined as 2x minus y, and g is defined as, I don't know, x minus 2y. So if I were to ask you what is f, the function f, plus the function g, well, that would be fairly simple, right? That's just combining like terms. You got 2x minus y, and you're going to combine that with x minus 2y. So what is that result? Well, that result is if you just drop those parentheses and combine like terms, we got 2x and x, we got 3x, and that's minus 3y, right? Now, the idea of the linear transform has two conditions in order to say that it maintains linearity from the transformation. So the first condition, and again, I'll use this FG language for just a second, is that, so in this case, let's imagine that there's this transformation function out there, okay? That it can transform G, it can transform F, but what would it mean to say that this function has the property of linearity? Well, the first condition would be this. That is, if you were to take the sum of f and g, right, just like we did here, and then transform its sum, you would get the same thing as if you were to have just transformed f and then transformed g and then added them, right? In other words, this simply means the transformation of the sum is equal to the sum of the transformations. Right? In other words, it doesn't matter. So imagine if I took this 3x minus 3y and then put it here and then transformed it. Well, I would have got the same thing if I would have as if I were to transformed f, then transformed g, and then added. I would have still got the 3x minus 3y if indeed you have this property of linearity. That's your first property. And I'm telling you, do not go to sleep yet. Okay, I promise you this is this is actually very beneficial. In just a second you'll see it. The second property and the final property, in order to have linearity, has to do with scaling, right? So just imagine there's some scalar, we'll call it A, So this property says, look, if you take, let's say, f, and you scale it, say double it, all right, and then transform what's left, you would have got the same thing if you would have first transformed f and then scaled it. So it doesn't matter if you scale first, then transform, or if you transform first and then scale. I used a 2 here. Let me write the a like I did on the left side. So it doesn't matter if you scale first, right? You can imagine, just doesn't matter if you multiply by a first, some scalar a, and then transform it, or if you transform first and then distribute an a. Doesn't matter, you get the same thing. So the transform of the scalar product is equal to the scalar product of the transform. These two conditions must be present in order to have this property of linearity. It just so happens, though, that Laplace transformations are linear transformations. So Laplace transformations do indeed have the property of linearity. So they have property of linearity. Right? In fact, the way you would really think about it is this whole Laplace, that is like this is what you would consider a linear operator, right? Is the way you would really think about it. But nevertheless, what does that mean? So in the language of Laplace, that would mean that if you had two functions, say functions of t, you could add your two functions and then transform them, or you could transform each one individually and then add them. Either way, you get the same thing. And now, just like above, you could also think about a scalar, some scalar c. So it wouldn't matter if you scaled your function first and then transformed it, or if you transformed it first and then scaled it. Same thing. Now, the proof of this is pretty easy, but I'm not going to go through that. Let me show you. I'll tell you what. I'm going to go ahead and take a break here, but let me at least write the problem that we're going to be doing when we come back from this break, and we're going to use that property to save us a massive amount of time. So let's assume for a second that you wanted to transform, let's say 11 plus 5e to the 4t minus 6 sine of 2t. All right, now imagine you have this really quickly. Imagine you have some second order differential equation, and the f of t, this non-homogeneous, is what we have here. Okay, so this is what you would have to be using your method of undetermined coefficients to. So let's keep that in mind as kind of an ultimate game plan. But when we get back from this in the next video, I'm going to show you how that property I was just going over, it's not just fluff. It actually it can be an extreme time saver, and we will do that when we get back.